Swayam Prabha. Digital India. Educated India.
Now we will look at an example of a circuit with inductors where the inductor currents can undergo instantaneous changes. Okay. Let's say we have a current IS and we have a switch like this. As I mentioned before, if you have switching action, that could be equivalent to stepping the values of currents or voltages in the circuit. And let's say this switch is initially short circuited and it open circuits at t equal to 0. Okay. And let's say we have these two inductors. Now first of all we will determine the order of the circuit, that will come soon. Now before t equal to 0, this switch is short circuited and all of this current flows into the short circuit, and all we have effectively is a circuit like this. Okay. And after t equals 0, we have the current source driving these two parallel branches. Okay. So let's say the value of this is Is. So we can think of basically solving this particular circuit because we want the solution for t greater than 0 and some initial conditions, some values of L1 and L2 are given at t equals 0. Okay. Let me for simplicity assume that the current through L1 and the current through L2 are both 0 just before the step current is applied. Okay, like I said, opening the switch is like applying a step current to this particular circuit. So first of all, what is the order of the circuit? So if I take the source free circuit, that is with the current source open circuited, what do I have? I have the single loop R1, R2, L1, L2, and this is of course equivalent to, you can see that these two inductors are in series, these two resistors are in series. So we have L1 plus L2 and a single inductor of L1 plus L2, and across that we have a single resistor R1 plus R2. And we know that if you have a single inductor in a circuit, it's a first order circuit, and the time constant of the circuit is the value of the inductance divided by the value of the resistance which is across it. Okay. So this will give you a time constant which is equal to L1 plus L2 divided by R1 plus R2. Okay. So this is how we calculate the time constant. We will now evaluate it formally and verify that this is indeed the case. Okay. So let me copy over this part of the circuit and write the differential equation. Now we will choose I1 as the variable. I1 is the current through L1, and by Kirchhoff's current law here at this node, I know that the current through L2 is Is minus I1. Now what is the circuit equation I am going to write? These three branches are in parallel. In particular, L1 and R1, the series branch is parallel with the series branch of L2 and R2. So the voltage across this branch and that branch are exactly the same, and that's the equation I am going to write. You can write it any way you want. You can write the KVL around this loop and so on. Now the voltage across L1 and R1 will be L1 time derivative of I1 plus R1 times I1, and that is exactly equal to L2 times the time derivative of the current through L2, which is Is minus I1, plus R2 times the current, which is Is minus I1. Okay. So, if I group all the terms containing the variable I1 to the left hand side, this is what I will get, and on the right hand side I will be left with okay, and I will normalize it so that the term without the derivative, okay, the 0th order term on the left hand side has a coefficient of unity. So, that lets me read off the time constant. So, I divide all terms by R1 plus R2. Okay. So, now this is in the standard form, and if this coefficient is unity, the coefficient here is the time constant, and it is exactly what we calculated earlier. Okay. That is the time constant, and this equation also tells us a number of other things. Like I said, what we have is a circuit in which this current Is is being stepped at t equals 0. It goes from 0 to some value. Okay, let me call that I naught. So, if I think of Is as a time varying function, it goes from 0 to I naught. Okay. So, the derivative of Is is an impulse at t equals 0. Okay. Now, I do not want to introduce impulses into our calculation and so on, and it is not necessary also. Just to find out what we want, we can simply appreciate the fact that this first derivative of Is is an impulse. So, this is an impulse, whereas this quantity which just has Is is finite. Okay. This already tells you that this I1 cannot be continuous. I1 also must have a jump, because if I1 is continuous, then the slope of I1 will be finite everywhere, and you can never balance an impulse on the right hand side with only finite quantities on the left hand side. So, the only way for this equation is to be satisfied is for I1 to have a step, which means that the first derivative of I1 di1 by dt is also an impulse. So, this part which is an impulse balances this part which is also an impulse. Okay. So, that is balanced by that one, and this part which is finite will balance that part which is also finite. Okay. This is just at the instant of the step. Okay. So, at the instant of the step, we have L1 plus L2 by R1 plus R2 times di1 by dt to be equal to L2 by R1 plus R2 dis by dt. Now, this means that this is just at the instant of the step. If I integrate both sides with respect to time, they will still be equal to each other between the same limits. 0 minus and 0 plus. Okay. So if I do this, this quantity is nothing but I1 of 0 plus minus I1 of 0 minus. Okay. And this quantity here is nothing but Is of 0 plus minus Is of 0 minus. Okay. And I'll of course have the same scaling factors on the two sides. So what this tells you is that R1 plus R2 in the denominator will cancel out. So we will have the change in current across the step, across the instant of the step, will be L2 by L1 plus L2 times the change in the source current. Okay. Now this is similar to what we had with capacitors. If you apply a voltage step across a series combination of capacitors, then across each capacitor you will have some capacitive ratio times the input step. Similarly, if you apply a step current to a parallel combination of inductors, then in each inductor you will have a step current, and the size of the step in each will be related to the ratios of inductors. Okay. So this you can calculate, and again, just like in case of capacitors, when we applied Kirchhoff's current law, at the instant of the step we could ignore the resistors, because if we had infinite currents in capacitors and finite currents through resistors, the resistor part won't contribute to anything and we can kind of neglect it. And that's what I have done mathematically here. I have tried to balance the left and right sides separately for the impulses and the finite quantities. So just like we ignored resistors in parallel with capacitors, in this case we can ignore resistors in series with inductors. So just for the calculation of current steps, whatever R1 we had here and R2 we had here, these two are ignored while writing KCL. That means that the voltage drops across them equals 0, that is, they are short circuited. And this makes sense again, because if you have a step change in inductor current, across the inductor you have an infinitely large voltage, and this is a finite voltage across the resistor, so we neglect it, similar to how we neglected resistive currents in circuits where capacitive currents were infinite. Okay. We have L1 and L2 and we have Is, and you clearly see that then the current divides in inverse ratios of the inductors. So through L1 we would have Is times L2 by L1 plus L2, and through L2 we will have Is times L1 by L1 plus L2. Just like we said that in a series combination of capacitors, the charge cannot go anywhere from the intermediate plate. The total charge there has to remain the same. Also, we can state a similar rule where the total flux linkage will remain the same in the inductors just across the step. Remember, all of these calculations are valid just to calculate the inductor currents immediately after the step. After that, the resistor voltages will be significant and you have to go from there. Okay. So I1, which is the current through L1 at 0 minus was 0, and I2 at 0 minus was also 0, and just after the application of the current step, this will be L2 by L1 plus L2 times Is, and I2 of 0 plus is L1 by L1 plus L2 times Is. Okay. So from these and the final values, which can also be calculated quite easily, for the final values in an inductor circuit, what is it that we know? voltage across an inductor equals 0. This is of course assuming constant or piecewise constant inputs. This is for a constant input. Okay, because then the inductor current also has to be constant, and if the inductor current is constant, the voltage across it, which is the time derivative of the current, will also be 0. So that means that all inductors can be short circuited for the final value calculations when you have constant inputs. So we have IS, and I will short circuit L1 and also short circuit L2. Okay, and we have R1 and R2. So this is a purely resistive circuit. So we know that the final values will be IS times R2 by R1 plus R2 over there, and IS times R1 by R1 plus R2 over there. Okay, so this also we know the time constant, so we can construct the final solution very easily. Okay, so I1 of infinity will be R2 by R1 plus R2 times IS, and I2 of infinity would be R1 by R1 plus R2 times IS. Okay, so from these and the time constant, we can write down the functions for both I1 and I2. I have assumed 0 initial conditions. So I1 of t, which is I1 of infinity plus I1 of 0 plus minus I1 of infinity times exponential minus t by tau, which this is of course the general form for any first order circuit, and I1 of infinity we found was R2 by R1 plus R2 times IS, and I1 of 0 plus is L2 by L1 plus L2 times IS minus I1 of infinity, which is R2 by R1 plus R2 times IS exponential minus t by tau. I will retain the symbol tau, but we know that tau equals L1 plus L2 divided by R1 plus R2. So this is the expression for I1 of t, and I2 of t is of course the same general form, I2 of infinity plus I2 of 0 plus minus I2 of infinity exponential minus t by tau. Tau is of course the same, and I2 of infinity is R1 by R1 plus R2 times IS plus L1 by L1 plus L2 times IS minus R1 by R1 plus R2 times IS exponential minus t by tau. Okay, so these are the solutions for I1 and I2 as a function of time, and if you have numerical values you can substitute these, and also we assumed 0 initial conditions just before the step is applied. If we do have non-zero initial conditions, then it is still quite easy. All we have to do is substitute the right values for I1 of 0 minus over there. Okay, so from there we can calculate everything. So that's how we calculate currents or any other quantity in a circuit where the inductor currents can have step changes. Okay.